Okay, continuing on with section 2.2, finding derivatives, which are instantaneous rates of change with y with respect to x. It also, the derivative would represent the slope of a tangent line drawn at a particular x value. What we saw is that just like from 2.1, this instantaneous rate of change is really this limit definition. And what I really want you to understand is that x is just a number. We plugged in a instead of x when we were dealing with section 2.1. That a value is whatever x value we'd like to evaluate that at. But also what we saw as we were introducing 2.2, we saw from just the other day that there was a wonderful shortcut if x was simply raised to a power. We could use the power rule to find the derivative very quickly without having to make use of a limit definition. We'll take a look at example 2. The absolute value of x is not written as x to a power. What we saw for the shortcut was if y was equal to x raised up to the nth power, the derivative, without having to resort to the limit, could be found as just bringing down that power and then multiplying x to the n minus 1 power. You're going to see that the absolute value of x does not fit this type of a function. So you might wonder, could we evaluate the derivative at x equals 0? The answer is yes. And what we're going to do is use this limit definition. In fact, we are forced to use this limit definition. We can't use the shortcut. And my goodness, as we're working this out, this will become f of 0 plus h minus f of 0 divided by h. And let's see what exactly is happening here. We can see that f prime of 0 then is this limit. Well, what is our 0 plus h? Well, substitute that into the absolute value. You've got the absolute value of 0 plus h minus, well, f of 0 is the absolute value of 0 itself. Oh my goodness. If we go back to our limit chapter, guys, you're going to know that we're in trouble in terms of this limit existing. Why? Well, we could take a look at the limit as h approaches 0 from the right. And remember what's happening with the absolute value of x or of h. That's going to be h or opposite h, depending on whether h is positive or negative. Well, if we're approaching 0 from the right, h is positive, we're going to have to choose h. So we'd get h all over h. That would equal 1. As we take a limit as h approaches 0 from the left side, the absolute value of h now would be opposite of h. And opposite of h over h will be negative 1. Therefore, this limit as h approaches 0 of the absolute value of h all over h does not exist. But what is it that we just found that doesn't exist? It's f prime of 0. That does not exist. We're not differentiable at 0. You can get a real nice visual. Look, here's the absolute value function. The absolute value function, of course, is y equals x when x is positive, y equals opposite x when x is negative. From the right-hand side of 0, we have a slope of 1. From the left side, we have negative 1. By the way, just like our limits would have shown us. At 0, obviously, you're at a corner, and your tangent line slopes would be different values. So it's very possible for a derivative not to exist Mainly because we have a corner, not necessarily because the limit is approaching infinity, or that we're having a vertical line that we've seen in the past. Okay, so let's take a look at what we will now note. Not every continuous function is differentiable. You know, the absolute value function was continuous. In a simple sense, we could draw it without picking our pencil up, but we saw that we would not be differentiable at x equals 0. Well, here's a theorem. We're not going to prove it, but if a function is differentiable, if a derivative will exist, then f must be continuous there. Well, remember that if a theorem is true, its contrapositive is true. A theorem would be P implies Q. The contrapositive would be that not Q implies not P. Well, what's the contrapositive of this theorem? Well, it would be if f is not continuous at x equals a. If it's not continuous at a, then f is not differentiable at a. So what we're seeing is continuity is a necessary but not sufficient requirement to be differentiable. However, when our function is not continuous, of course that means we're not differentiable. So if you're continuous, you might or might not be differentiable. If you're not continuous at a given x value, there is no derivative. The derivative, of course, cannot exist. Okay, we can talk about derivatives from the left side and the right side as well. Let's say that you're looking at a closed interval from a to b. We could approach a from the right. Imagine that we were looking at a number line where we had a and b for our x values. You could certainly approach a from the right side. Well, remember, f prime of a would have this definition. If you wanted to take your derivative of a, you could only approach it from that right-hand side. So this is a right side derivative. It would be a tangent line slope or an instantaneous rate of change at a, but only from the right-hand side. Also, what we can see is that this second derivative would be a left side derivative. Evaluating a derivative at b, you could only approach b from the left, and this, of course, is what f prime of b would be equal to. I could even write that out in front. So, to be differentiable on a closed interval means that your derivatives exist from the right side and the left side at your endpoints, as I've just described, and that you'd be differentiable at all points on the open interval. Okay, now in our example 2, we saw that at a corner, like the absolute value, our derivative does not exist. Corners are where f is continuous, but the derivative does not exist. That is, the right side and the left side derivatives at that given x value exist, but they're not equal. You can see perhaps that we might have a slope of 1 and negative 1, like we might have in an absolute value at a given corner point. However, your corner points would not necessarily have to have opposite signs. I wanted to point out the second picture. That maybe from the left side of a given x value you have a slope of 3. From the right side you'd have 4. In any event, the tangent line slopes would not agree from the left and the right. That would require the derivative not to exist. What about a vertical tangent line? A vertical tangent line occurs if f is continuous at a given x value, but the derivative as x approaches a in a limit in absolute value would approach infinity. And you can see this little picture right here indicating that. So you want to realize that you learned in Algebra 1 even that vertical lines have slopes that are undefined. You might remember Vux and Hoy. M is undefined, or undefined, as we joked around in class the other day. So, you know, that's where that infinity is coming into play. It might be from the right side and the left side. You're going to be in agreement with a positive infinity and a positive infinity, but you might even have different signs. We're going to see in just a moment that that could happen. Take a look at this next example. Here's a graph of f of x, radical x minus 2. Let's think about x files. We're going to move 2 steps to the right of this square root function, and it would look something like so. And I guess what I want you to see is just using the graph. Right now, if we took a derivative, we'd have to use the limit approach, because with that x minus 2 in there, we'd have some trouble with a power rule. If it was only radical x, we could get away with it. But look, you can see that it looks like we have a positive tangent line slope. Look what's happening as we get real close to 2, though. Looks like our tangent line is becoming more and more vertical. And it certainly is. What do you think our domain would be for f prime of x just using a graph? We would hopefully say we would think that x would have to be bigger than 2. Okay? We're going to learn very soon how to take that derivative in a couple of sections. Okay, a cusp. Well, a cusp is like a picture that I've just shown here. F is continuous, but from the left side or from the right side, you will approach positive infinity. When you go in the other direction, you will approach negative infinity. So one side, as we approach A, will go to positive infinity. On the other side, will go to negative infinity. This is still going to represent a vertical tangent line. We're going to talk about why in just a second. But look, from the right of A, this picture that I've just drawn, you can see my tangent line slopes appear to be greater than 0, positive. As I get closer and closer and closer, it looks like I'm going more vertical. Looks like I'm approaching positive infinity. Look what's happening as I approach A from the left, however. You can see in this green little segment right here, or now I'm tracing over in blue, it would appear that we'd have a negative tangent line slope. And it's becoming more and more vertical, so we'd be approaching negative infinity. You can see we have different signs of infinity. This would be called a cusp. We're also going to say that there is still a vertical tangent line there. Now why? If you look back on the notes that we saw earlier, we've got a vertical tangent line if the limit as x approaches A, let's maybe get a little swiggle here, the limit as x approaches A of the absolute value of f prime of x equals infinity. Well, hey, put absolute value around your derivative, and negatives turn into positives, and positives stay positive. So this would be a vertical tangent line. Okay, so you get, for every cusp, you could technically say there's a vertical tangent line. Now there's one more problem that we can take a look at, but it looks like we're running out of time, and I'm going to have to continue it on a second part of the video. But it's just asking a question for this function, 1 plus x to the 4/5. Does f prime of 0 exist? If not, is there a cusp? Well, tell you what, how about we use a shortcut. Derivative of 1 is 0, bring down 4/5, subtract a 1, 4/5 minus 1, you get negative 1/5, and then we can bring that down. We're going to investigate whether we have a cusp very soon.